To recap about random variables, they are used a lot in economics. For example, a random variable could be stock price. You don't know where it's going, and so it can be a variable based on time. And so it's best to get used to them as soon as possible because they come out everywhere in all sorts of journals. Okay, so PMF, probability mass function. Probability mass function is basically a function where if we're given, let me erase CDF for now, we are given a random variable x, and x can be, the space of x will be D, and there can only be 4 possibilities because x was defined as the number of heads, right? And therefore, the probability that x can be a certain value, that x can be an x where x is in the space, this is what the probability mass function is. So before I wrote it down without explaining what it was, this is the definition. We use small f for a reason. Notice that this function largely depends on the random variable that we're talking about, and so we add a subscript to it, as opposed to another random variable and another PMF that could be defined like that. And for this, the domain would be everything inside the space. So now, hopefully it's clear that the PMF can be labeled as 1/8, 3/8, 3/8, and 1/8. So now we're going to talk about the CDF. CDF is used with a capital F. It's also used, the subscript large X is used, where X is the random variable that we're talking about. But this time, the CDF is the probability that the random variable is not equal to X, but less than or equal to X. So in this case, our CDF function would be 0 for all x's less than 0, 1/8 for our values of x between 0 and 1, because the probability that we get exactly 1/8 happens at 0. That's why this is the only place where there is a mass. But we're going to try and make the domain continuous. And therefore, if we consider the next boundary between 1 and 2, then we're going to add 1/8 with the 3/8. So we're going to add these two. And we get 4/8. For the next values, between 2 and 3, then we add another 3/8. And we get 7/8. Finally, for every x bigger than 3, bigger than or equal to 3, then we'll always have 1. So the probability that the number of heads is less than or equal to 3 is 1. There is no way that it'll be more than 3, right? That's what this is saying. The probability that x is less than or equal to 2 is basically the probability that x is 0 plus probability x is 1 plus probability that x is 2, right? So I added the first 3 and I got 7/8. Even if I made the 2, this 2, if I change this into, for example, 2.5, still the arguments are the same because there are no values of the number of heads that we can take on between 2 and 2.5. You can't have 0.5 number of heads. So that's why I said all values between 2 and 3, instead of just saying 2. And I can draw the CDF like this. Let me draw it better. So for if x is less than 0, then our CDF is 0, right? So our CDF is going to look like that for every x less than 0. For x is between 0 and 1, 0 and 1, our CDF is going to take the value of 1/8. Between 1 and 2, it's going to take the value of 4/8, 1/8 plus 3/8. So it's closed here and open here. Between 2 and 3, it's going to be 7/8. Finally, from 3 onwards, value is going to be a constant 1. Notice that we always have a closed value if we approach from the right. We say that CDF is right continuous. Hopefully you remember from calculus that a function is continuous if and only if it's left continuous and right continuous. Right continuous means the limit as x approaches the value from the right side is going to be the value there. So right continuous means. But it's not left continuous. It doesn't have to be left continuous. Okay? And maybe we can do another example, or maybe you can do it yourself. Let's say that my probabilities, okay, so sometimes I'm going to use px and sometimes I'm going to use fx. In literature, usually if it's a discrete random variable, then this PDF fx is also written as px of x. Okay, so both of them mean the PMF, so you just have to be wary about which variable to use. I'll try and stick with the small f because we'll soon find out why. So sorry about the confusion. Fx of x is going to be equal to x divided by 6 for x in 1, 2, and 3, and 0 otherwise. First of all, we have to check that this is a probability mass function. We have to check that this is true. So we need our probability mass function to never be negative, because probability cannot be negative. And also, we need the sum of all values to equal 1. Okay, let's check that this is 1. Well, obviously, 1/6, 2, and 3 add up to 1, right? So this is a probability mass function, and it's 0 everywhere else, so it adds up to 1. And now, if you want, you can try and figure out what the CDF is. Okay, so do it yourself. The hint is for x between -infinity and 1. Obviously, it's going to be 0. And then the first one is going to be 1/6 between 1 and 2. And then find out the rest. draw it like I did here. Draw. So tomorrow I'll show you what the answer is. It's not going to be hard. It's just to check that you understood the different notations. Okay, so let me write that down. Homework on page 27 of notes. Okay. Next, we talked about discrete random variables. Now we're going to talk about continuous random variables. And the definition is as follows. A random variable x is a continuous random variable if the CDF that we get from it is continuous. Notice that for discrete random variables, there were jumps here. There were jumps. And so the CDF is not continuous. But for continuous variables, by definition, the CDF will look something like that, where the limit as the CDF approaches infinity is 1, and the limit as the CDF approaches negative infinity is 0. Okay? And furthermore, so for the PMF, for the CDF, when we're doing a discrete random variable, what we did was we added the values, right? So to find this value right here, I had to add every value less than or equal to 1. So what I did was I added these two values. Similarly, for finding this one, I had to add everything less than or equal to that. And I could add it because there were jumps, because there were masses at 0, 1, and 2. So for example, from the CDF, I can even find the masses at here. I can calculate f at 1 by saying that it is fx of 1 minus fx of 0, which is 4/8 minus 1/8. Anyway, what I'm trying to get here is that in a continuous random variable, I can't add. I can't add these because for each of them, the masses are 0, and therefore we don't have a PMF. Instead, we have a PDF. Okay? So in a continuous random variable, the probability that a random variable is at a certain A, okay, this is going to be 0 for any A. Furthermore, I can write my CDF as an integral. Notice that before I added everything between 0, to find fx of 2, I had to add the probability that it's 0, that it's 1, that it's 2, but I can't do that anymore, and so I'm going to integrate. Integrating is basically adding. It's a sum. It's an infinite sum. It's the limit of an infinite sum. And because of this, by the fundamental theorem of calculus, we see that if we derive our CDF for a continuous random variable, then we'll get the PDF. That's why I use big F and small f, because in calculus, usually f prime is equal to f, right? But we could have said p for probability mass function, but anyway, it depends on the literature, so you have to be careful about the notation. So in a continuous random variable, the probability that x is a certain value is 0, but there is a possible way of finding the value of x being between an interval, f8, between a and b, and that'll be CDF at b minus the CDF at a. Okay, and using this equation, I can say that this is the integral from negative infinity to b minus the integral from negative infinity to a. But we know that minus an integral is the same thing as adding it, but then we're switching it. And so this is really just the integral from a to b of, okay, let me write down the steps. Okay, so we have negative infinity to b plus, I'm going to switch the top and the bottom. Okay, a to negative infinity. But notice that these two are the same, and so I can combine it to get the integral from a to b of fx t dt. Right? And also notice that the probability that our random variable, because our random variable is a function going to the reals, the biggest it can be is infinity, smallest it can be is negative infinity. Notice that this is just fx of infinity. I should write a limit, but I'm not going to. Minus fx of negative infinity. And if we plug this into our integral, then we'll see that this is the integral from negative infinity to infinity minus the integral from negative infinity to negative infinity. This is 0. This is 1. And so it's 1. We are absolutely certain that our x lies between negative infinity and infinity. I'll give you an example of a continuous random variable, and this is used often. Let's say you're waiting for a bus, and the bus arrives every 15 minutes. And in statistics, we're later going to talk about what a uniformly distributed random variable is. But in other words, I can write uniform x. If x is the waiting time, then x is uniformly distributed anywhere from 0 to 15 minutes. So on the graph, I'll have that. To find the PDF, I have to think about the integral and when that becomes 1. So remember that if I integrate everything from negative infinity to infinity, I have to get 1, right? But we have the same probability everywhere because it's uniform. And therefore, we just need to find out the area underneath the curve between 0 and 15. So really, we're just going to do the integral 0 to 15 and of this function. But if you think about it, we don't even need to do an integral. We can if you want to, and we will find the answer. But because 1 is the area and 15 is the length, the height is going to be 1 over 15, right? Then if we multiply the two, then we'll get 1 as the total area, which is what we want. Okay, so if this is my waiting time, and this is my probability density function, then what's the probability that I get to wait less than 3 minutes? For that, this is the CDF, and so instead of going from negative infinity to 3, I can just go from 0 to 3, because every value between negative infinity and 0 is going to be 0. This function is 1 over 15 for everywhere from 0 to 15, and 0 everywhere else. So even if we integrate it, we're going to get 0, and so I can simplify the boundary. And if I integrate this, and the PDF is obviously going to be 1 over 15, a constant value, then I'm just going to get x over 15 from 3 to 0, so the answer is 1/5. So the probability that I wait less than 3 minutes is 1/5, which should make sense if we divide it like that. This is the area that we're interested in, divided by the total area. Okay, next, let's think about the expected value. The expected value of a random variable, which is sometimes written as mu for mean, Greek letter mu, is going to be either the summation of all x's for the PDF, for the PMF, sorry, if x is discrete, or it's going to be the integral for all reals. And this is going to be if x is continuous. And so let's think about the expected value of our waiting time. It's a continuous random variable, but we only need to integrate from 0 to 15. I know that my PDF is 1 over 15, but by definition I have to multiply x to it. And if I integrate this, then I'm going to get 1 over 15, x squared over 2, x goes from 0 to 15. Notice that if I plug in the 15, then the 15 squared cancels out with the 15 on bottom, and I'm left with 15 over 2. So about 7.5 minutes. What this means is that on average, I can wait about 7.5 minutes before the bus comes, or 15 over 2. 15 over 2 is exactly half of this. This is 15 over 2. Hopefully it's intuitive that we wait about that much, right? And the calculations show. So, okay. Maybe we can do one more expectation problem. Remember the number of heads. Let's say y is the number of heads in 3 flips. And what's the expected number of the number of heads? What's the average? For this, remember the value is going to be the sum of all y times f y. And so y can be 0, 1, 2, or 3, and so we're going to add all of them. And when we do, the first one is just 0 times something, so it's 0, plus 1 times the probability of getting exactly 1 head. Hopefully you remember that this is 3 over 8, plus 2 times the same probability, plus 3 times the probability of getting all 3 heads, 1 over 8. Okay, and this will be the expected value of y. Okay, after talking about expected value, usually you learn about variance. So this this is how variance of a random variable is defined. It's defined as the expectation of our random variable squared. Wait, sorry. It's not. It's the expected number of the random variable that looks like this. Okay, so if this is your first time looking at expectations, then this might look very daunting. But if you think about it, the expectation is a function on a random variable. But right now, expected value of x is a fixed number. It's fixed at the average of x. But because x is random, x minus a fixed number is also random. And so what we have inside here is a random variable. And it's being squared, but if this is random, then what gets squared is also random, right? Usually it's random. And so what we have here is another random variable, and we're calculating the expectation of that. If you think about it, we're calculating the deviance. For example, if this is the probability mass function of x, and this is the mean, as we saw before in the bus waiting problem, then x minus mu is really, if I wait about 10 minutes, then my deviance from the mean is going to be this much, right? My deviance from the mean, if I wait only 5 minutes, is also going to be this much. But if I don't square it, then the deviances add together when we're calculating the average, and they cancel out. And so my variance becomes a 0 if I don't square it, if I define variance in another way. And so we must square it to make it a positive number. Because here, x minus mu is positive. Here, x minus mu is negative, right? 5 minus 7.5 and 10 minus 7.5. But we only want to add positive numbers, and that's why we square it. Well, you might ask, why didn't we do something like a fourth or x minus expectation of x and then take the absolute value? We can, and there are some people who do use these techniques instead of using that, but that's no longer called variance. And also this squared has a nice property where in more advanced statistics you will learn about differentiating it. And differentiating absolute value is harder than differentiating a square. And so later on, or maybe before, you might remember that back in undergrad, if you took a statistics course called regression analysis, where we try to minimize the error when we do y is alpha x plus beta. We try to minimize this. And in economics, it's also used in, for example, econometrics, where we have data, right? You have like a scatter plot. And it looks like there's a trend, but it's not a perfect line. Okay, we're trying to find the best fit line. Y is alpha x plus beta. A best line between the two. And we find that by minimizing the distances between the line and the points here. And when we do this in econometrics, then we will find that defining it with a square is much better than defining it with an absolute value or some higher power, even though these are sometimes used. So I'm going to erase these. probably all know this, I'm just talking. Okay, so that's variance. And so variance is, I'm going to write it one more time here, x minus expectation of x squared. But I'm going to claim that this is the same thing as expectation of x squared minus expectation of x squared. This is taught in every intro to statistics courses, and this is easy to prove. First, I'm going to expand what's inside. And I didn't say this before, maybe I should have, but expectation is linear. What that means is that for a linear function, if L is a linear function, and I have A plus B plus CX squared, something like that, then I can separate this out into L of A plus B times L of x squared plus C times L of x. And the linearity of expectation is easy to prove, but it's just a lot of hard work. I mean, you have to write a lot, and so I'm not going to do it here. But basically what it means is that any constants can move out. And we can separate the addition into addition on the outside. Okay, so I'll erase that and apply that reasoning here. So because of linearity, we have expectation of x squared minus 2 times, notice that expectation of x is a fixed number just like 2, and so it goes outside the expectation. And what's left inside is this one, plus the expectation of x squared, and then we're taking the expectation of that. But the expectation of any fixed number, a, if a is a real number, it's fixed, non-random, then expectation of a is just a. And notice that expectation of x is fixed, therefore what gets squared is fixed, therefore I don't need to write an expectation here, so I'm going to erase it. Okay. And I have expectation of x squared minus expectation of x squared. This is called the kth moment. This is the kth moment. So variance is really the second moment minus the first moment squared. Okay. When we have a random variable x, then the mean tells us a lot about the random variable. For example, if you look at the bus sign and it says you can expect to wait about 20 minutes, and another bus you expect to wait around 15 minutes, right? But then also on the bus sign you see you expect to wait around 20 to 21 minutes, or on this one you can say you expect to wait around 15 through 24 minutes. Then it looks like this has higher expectation, but the second bus has much higher variance. And so this is more reliable than this one, than the other bus. So when we're given a random variable, the 2 points, mu, which is the expectation, sigma squared, which is the variance, tell us a lot about the random variable. So these are just two characteristics about the random variable that's given to us. So moments are used a lot in statistics, and so we'll just do one more and end class for today. We'll talk about, I'll just define the MGF, but then I don't know if we will have time to do this today. Okay, this is called the moment generating function of x. Okay. Based on my syllabus, we were supposed to do, right, we're supposed to cover joint, marginal, and conditional. I don't think we can do everything based on the speed right now, so we might have to give up some of these and do other stuff. I hope that's okay with you. But I'll try and cover everything that you need to know for the first semester of grad school. In the probability area anyway. Okay, so this is the MGF, and notice that based on our definition of expectation, this can be the integral. Oh, did I not define the expectation of g of x? Okay, so before this, let me define something. So remember that expectation of x is going to be either an integral or a summation, but I'm just going to stick with an integral. The integral of x times fx of x, right? dx. But I can, because x is a random variable, if I have a function g, which is non-constant, and I apply g into x, what this means is that, remember, random variables are functions. Random variables are functions going from a space into the reals. Now, if I have g of x, then I'll have g of x going from the omega to the reals into the reals. And so really g of x is a function going from omega to r. So g of x is another random variable where g is just a function going from r to r as long as certain properties are satisfied. And we can talk about the expectation of g of x. That's just going to be the integral of g of x times fx of x dx. Okay, so based on this idea, I can find out what the moment generating function for e to the tx is. I just plug it in, and then the rest I just treat as an expectation. Either this or it's going to be that, right? For all x. Okay, what's special about the moment generating function? Looks like I'm not going to be able to finish in time because I have a lot to talk about the MGF, and so I guess we'll start tomorrow, starting with the MGF. If there are any questions, then you can ask me right now because we still have time. Are there any questions from today? You can also ask about the MGF. No? Okay, we'll end the class today. I'm going to try and save the notes on PDF.